Hello everyone. My name is Tahani. I'm a postdoc at the University of Glasgow. My field of expertise is AI and data-driven solutions. Today I'm gonna to talk about Today I'm gonna to talk about AI-driven thermal prediction for enhanced reliability in 3D high bandwidth memory chiplets.
Tahani, I think you're not sharing. Sorry, we cannot see your share screen.
You can see my screen now?
Not yet.
Just 1 second. You can see it now.
Yes,
Can you see it now?
yes.
Yes, perfect. Sorry about this. Yeah, so first, why 3D high bandwidth memory matter for modern AI accelerators? When we talk about modern high-end AI accelerators, such as GPU or AI accelerators, this kind of technology heavily rely on 3D high bandwidth memory to meet the bandwidth and energy demand for high performance computing, data-centric application, and advanced AI workload. What kind of the advantages that high bandwidth memory can provide for these kind of advanced applications? First, high bandwidth memory provide with vertical stacked multiplied DRAM die in 3D stack or 3D structure, and also provide with low latency, low power consumption, better energy efficiency, and higher capacity. So in general, we can say high bandwidth memory is a key technology that enable advanced models like large language model deployment and development. And it's also important for any AI or deep learning model that must process very large amount of data as fast as possible. So when we talk about the high bandwidth memory architecture, it's not a new kind of memory. It's about how we deploy the DRAMs or memories in the system. So, for example, when we talk about this stack of memories, we can see this as a 4 high bandwidth memory from the top to the bottom. At the first, we will have from the bottom substrate, a silicon substrate at the bottom. Then we will have 4 chips or memories. These chips or memory include through silicon vias structures in each chip or each memories. And also these kind of memories will be connected with each other through bonding layers. And at the top, we will have the heat sink or cooling conditions to have like air cooling, liquid cooling, or physical change cooling. This is for high bandwidth memory, but we could have 8 layers or of memories, or 4, 2, 1, or more. So when we talk about the high bandwidth memory stack, it's considered more complicated than the DRAM chips or the traditional methods, because we deal with 3D architecture and the connection is sophistications. So in general, we can say it's important to have thermal management to ensure high bandwidth memory technology can operate with the safe thermal limit and thereby maintain high performance in the demanding computing environment. Also, when we talk about thermal management challenges in the high bandwidth memory, we will have the problem is the high power density with stacked chips, especially in the middle layers, that can creating a localized hotspot, which can causing something called thermal stress in the materials and perform degradation and reduce reliability if it is not controlled. Also, we could have another problem, which is the thermal conductivity of the material used in building TSV. It's often insufficient and resulting in building up heat that affect the whole system performance. So these challenges require efficient thermal design solutions that require the integration of advanced predictive technology to ensure optimal thermal performance. Actually, there are many classic optimization techniques have been used to optimize thermal performance for high density chip stacks. But these methods are not enough. Why this method they are not enough, we will see now. First, we will talk about the traditional finite element analysis. This is considered very good and very accurate for simulation heat conditions. But it's become computationally intensive when we talk about large and complex system like 3D stacks. So also it's considered very slow when we talk about the simulation. We will try to explore and optimize different solution space. There is another method can be used as well, which is faster simplified model. This kind of model tends to rely on simplify the model to do some task, but actually it's considered lower accuracy, especially when we talk about 3D structure and TSV configuration. Accordingly, we can say in general, it's hard to optimize thermal performance for high density chip stack. And also the hotspot and reliability issue may be missed until later in the design flow. So we will talk about the data-driven and AI solution. Data-driven and AI solution is not a new thing. It's applied in different fields, and we will see how we can use it here for optimization goals. Data-driven with the neural network can learn from the finite element analysis data to optimize, to compute a complex non-linear thermal behavior and hotspot position with high accuracy. It also can provide with fast prediction to enable thermal optimization of advanced high perform memory architectural. Based on this paper that called Neural Network Surrogate Model for Junction Temperature and Hotspot Position in 3D Multi-Layer High Bandwidth Memory Chiplet under varying thermal conditions, we will show how data-driven neural network can act as a thermal prediction model for 3D high bandwidth memory structure under varying operating and cooling conditions. First, when we talk apply AI-driven solution or deep learning models for solving such kind of problems, we need to have data. And the best source to have the data, it will be the thermal simulations, such as finite element analysis to build a 3D hyperparameter architectural. Then we will use this we will do kind of data preprocessing for the thermal simulation and for the neural network to work on this data. Then we will see the neural network architectural and training. Then how the prediction temperature and position work. First, when we talk about the data source, it will be from the thermal simulation. Actually, according to the paper that we talked about, they used INSYS to run many 3D thermal simulation of high bandwidth memory stack and detailed 3D high bandwidth memory models like substrate, chips, TSV regions, and the heat sinks. And also they used thermal solver computes the full temperature distribution, include the junction temperature and the hotspots. Actually, as we said, we need to have like thousands or 10,000s of samples. So they used Python script to make this process automated to generate samples or simulation forms from the INSYS apps. So for every iteration with the Python, they try to switch the high bandwidth memory structure and also the power, chip thickness, TSV, material of thermal conductivity, and HTC. So then they launch the simulation automatically. After that, they will get the expected or extracted result as a junction temperature and hotspot positions. It will be something like that. This like the Python script with the INSYS. They will iterate through a different number of high bandwidth memory layers like 1, 2, 4, and 8. And also the layer thickness, it will be changed from 10, 30, 50 with maximum number 700 to 720. Then also the materials properties and TSV pattern, it will be changed with each round, the power value, calling conditions. All of these simulation, it will be used to produce large data set to be used for the neural network model training. So for each of this combination, one thermal simulation, it will be considered one data point for the neural network training. For example, here, each of this simulation, it will go through a neural network to predict to output junction temperature and hotspot positions. For the data processing, we will have two kinds of data processing. Data processing for the simulation itself and data processing for neural network. For the data processing for the simulation, in general, when we talk about all the possible combination of high bandwidth memory structure, the number of cases it's exploded as we add more layers. The number of cases or the combinations can arrive for million or even billion of simulation, which is impossible to simulate all of these cases. For example, when we talk about 8-layer model or architecture, for each of these layers, we have 4 group of parameters. The first chip thickness, we will have the logic and 7 memory layers. In general, we will have 8 layers. And for the TSV or chip thermal conductivity, we will have also 1 logic layer and 7 memory layers. In general, we will have 8. Also for the power, we will have 1 logic layer and 8 memory chips. In general, we will have 9 layers. For the cooling, we could have top and bottom surface, 2 sides. And in general, we will have 27 parameters, which, and all of these parameters, it will be with 3 possible values, low, medium, and high. In general, we will have like 3 out of 3 power to 27, which almost 7.6 million trillion combination, and it's not easy to simulate such a number in INSYS. So we need to reduce this number, but with an efficient way, and also to include all the important combinations. There is a method called sampling method. It's called partial Latin hypercap sampling. This method, it can go through all of these combinations and select the best, like according to the percentages that we define. It can select like few thousand of samples rather than trillion or billion that can cover all the parameter spaces. After removing the non-physical result, we could have 30,000 simulation. It's become a nice number for building neural network. And also having like 1,000 simulation, it's reduced the simulation time and still provide us with all the required informations. After the simulation, we expect to use this data for training a neural network model. But actually, we need to do some pre-processing to make the data fit very well for the model. For example, we need to do some normalization for the input data to have all the data in specific range between 0 to 1 or between -1 to 1, rather than having like a huge difference between the values. So here they use the normalization for thickness, power, HTC, temperature, and other factors to have it like in the same range. And also, when we talk about different structure of layers, like 1, 2, 4, 8 layers, that means we will have different number of dimensions. If we have 8 layers, we will have different dimensions number compared to having 1 or 2 layers. So they did something called placeholder to fill these places with -1 to have all the dimensions equal for 8 layers, 4 layers, 2, and 1. Then, as usual, deep learning models, we will split the data for training. The training, it can be like 80%, most of the data used to the training, and 20% or less for the testing the neural network. According to the training process itself, we could have two kind of architectural to train deep learning model that can predict both junction temperature and the hotspot position. First, architectural, something called one neural network, two outputs. For this kind of neural network, we could have single neural network that can predict two output structure. This kind of architectural consider very nice to enhance computational efficiency and reduce redundancy parameters. And for more complicated scenarios or to get more accurate results, we could need to use two neural network, one neural network for junction temperature and another neural network for the hotspot position. In general, when we have two neural network, we expect to have the junction temperature neural network to be more smaller than the neural network used to the hotspot position because the temperature it's more easy and more smoother, and also it can be solved by using linear activation. But for the hotspot position, we could need to use more layers and using non-linear output activations. This is the first architectural. As we can see, every combination, it can be as a one input for the neural network. And for one neural network and two outputs, as we can see here, the first branch, it will be the temperature. It will be finished its training after the first hidden layer, because we don't need to make this go deeper, because it's very simple and it can be predicted by one layer. And for the second branch, which is the position, it's need to will train or more deeper trainer, so it will go through 4 layers, and both of them will go through the mean square errors. As we can see here, for the temperature, we will measure the mean square error, and also for the position, we will compute the mean square error. And for the position, we can multiply with specific factor like 10 or any numbers as a way to reflect the importance of this value. For the two neural network architectural, we could have one simpler neural network for the temperature with the 3 layers, and one with more layers to the position. And also we can apply the dropout here to avoid the overfitting. And the advantages of this network, it can give better accuracy. So according to the perform comparison for two neural network and two outputs, it's give better temperature, because the temperature has like different model with more layers, and it can give like some better result. But for the position, it's not it's give like worse result than the one neural network two output. So for the one neural network and two outputs, it's give better position prediction, but it's like a little bit lower in the temperature. According to the comparison or the result comparing to the simulation, which is the accurate result or the main baseline, this figure show one high bandwidth memory with 1 layer, and high bandwidth memory with 2 layer, 4 layer, 8 layers. And for the blue circle, we can, this is the simulation data, and for the star, it's the prediction. As we can see here, the prediction by the neural network and the simulation, it's almost the same, and the model can predict this temperature and position with high accuracy, similar for what we can get from the simulation with the faster implementation. So, and also here, they try to measure the generalization of the model according to unseen data. So for the blue circle here, it's the prediction, and the green star here, it's the simulation. As we can see here, the model prediction, it's very close to the simulation, even for the unseen data, which means the model can generalize very well for unseen cases. In general, we can say we can build a data-driven neural network model to predict the junction temperature and the hotspot position from the key design parameters like layer thickness, TSV conductivity, and power HTC. So in general, this neural network model, it can give like about 98.4 accuracy compared to fine element analysis, which is considered very huge accuracy with a few like seconds or few minutes to have this model done. And also this kind of model, it can generalize very well for only unseen data. So also this is considered very helpful because it's very fast. So this is the final slide. Thank you very much.
Thank you, Tahani, for the talk and the presentation. So I think I will give the floor to Alberto. I think we can, everybody who has a question during the talks, you can just put it on the Q&A section, and then we can discuss it at the end. So Alberto, I think the floor is yours.